here we are. We have to talk about rolling motion. We have to talk about it because it's so fundamental in so many machines that you deal with. Just the basic idea, sounds very simple, of a disk, and it's got some radius. I'll call it big R because I'm into big R lately. And it's just rolling along, and it's got some translational velocity v. And we just want to describe that motion. Well, it turns out it's a very complicated motion. Rolling motion is not simple at all. So here is a wheel, and I'm just going to roll the wheel, and we're going to keep up with the position of a few spots on the wheel. So if I put it here, I'll start it about here. And I'm just going to roll it along the bench. Here we go, and it goes, and it goes. So now, if you were to track the position of one of these orange, or these green pieces of tape, here's what it will look like. So there you can see it's making a cycloid. It's called a cycloid path. So that's a pretty complicated path. That's a lot more complicated than just a wheel moving, right? Another way I can show you how complicated it is imagine one small piece of the motion about here. And now let's keep up with the bottom and a piece at the middle and at the top. And what you see is as it rolls, the bottom stops. The middle moved along about at the speed of the wheel, and the top's actually going faster. So the different parts of the wheel actually are not going the same speed. They're going different speeds. So what this means is tracking the individual elements of a wheel, and while it's moving, very, very complicated. Okay, so we don't actually do that. There's a simpler way to treat rolling motion, and that is to treat it as the sum of center of mass. I'm going to put COM because I don't want to write out center of mass, translation plus rotation. And then it's not quite so complicated. So if we were going to do an energy problem, then what we would say is, let's think of the center of mass as being at the center axis of rotation. Let's assume it's a symmetric wheel. And this velocity we talked about, v, that's really v of the center of mass, because that's how fast the whole thing is moving. But we know also if it's going this way, then it must be rotating around. It must have an omega. And of course, omega's vector is actually, well, that's omega's vector. Omega would be pointing in. But omega is going around, velocity is moving along. So you could start to think about, in terms of energy, you could write that the k translation, that's the plain old k that we're familiar with, is 1/2 mv squared, where v is the center of mass, and m is just the mass of the entire disk. And k rotation is, we know, 1/2 I omega squared, where I has to do with the mass of the disk and how it's distributed. So if it's just a uniform disk, it's 1/2 mr squared. And omega is just how fast it's spinning. So if you use these to solve problems like before, when I had the wheel roll down the hill in the previous board, and we said, how fast is it going? We know it had an energy mgh. All that was given to kinetic energy. But here we have two kinds of kinetic energy. So it looks like we can't solve it, but we can, because v, the center of mass, and omega are related. As this thing rolls along, the translation is tied directly to the rotation. You can't help it, because if it's rolling without slipping, if you think about it, then omega is how fast it's going around. Well, it makes one entire circumference every period of motion. Okay, so an entire circumference is 2 pi radians every period. We know that's true. But how fast is it going around? Well, it has to do with the velocity, right? It has to make a period in the time it takes the thing to spin around once. Well, that's the center of mass velocity divided by that's the circumference divided by the center of mass velocity. So we replace t with the circumference, 2 pi r, divided by v com. So I divided the numerator, or the denominator, by v com, which put it in the top. And really, that's just giving us our simple uniform circular motion formula, that omega is related to the velocity by v center of mass over r, because we're using big R. Okay? So actually, you do have a relationship for rolling motion between this and this. So you can actually divide out and figure out how much of the energy went to translation, how much of the energy went to rotation. So this is usually how we approach this kind of problem. And then you can think of it as the total kinetic energy. K total is, of course, we have conservation as the sum of the translation plus the rotation. But they are mathematically linked. You can also think of this in an interesting way with vectors that looks kind of nice, is you can say what we're saying here. Let's think back now to the 3 pieces of tape we watched. And let's do some vector addition on their velocities. All right, so we said we watched a piece of tape down here, we watched a piece of tape here, and a piece of green tape there. And we said, what are they doing? So now let's say, well, we're going to treat this as translation plus rotation. All right. So if we just consider translation, the thing is just moving forward, then all 3 pieces of tape would have been moving forward at V center mass. Right? We pretend it's just not even rotating. It's not spinning at all. Just translating along, V COM, V COM, V COM. Okay. But what if we consider just pure rotation? That was the fact that it's going around at omega, and if that's the case, then you have no velocity here, right? If this thing is just sitting here spinning, no velocity, this would go back at VCOM, and this would go forward at VCOM, at the velocity of the center of mass. That would be the pure rotation case. If it's going to rotate at this rate, it needs to rotate to make it move like that. This is how fast the M pieces would be going. Okay. So if you add those two, if you just add the vectors, let's see what you get. Here you get twice VCOM. If you add these vectors, you get the velocity of the center of mass right where it should be at the center of mass. And if you add these, they cancel and you get nothing. So it actually does give you exactly what's really happening. If you think of the disk, a column of the disk, as it's rolling, it's really falling over, right? And the top is going the fastest, the center is going half, and the bottom isn't moving. So this is our shortcut to deal with the complication of rolling motion as we break it up into 2 different problems.